Hello and welcome to the second episode in the Breadboard Apprentice series. In today's episode we are going to look at the clock module and how we can generate both the variable frequency clock and the high frequency clock using an oscillator, and also the single pulse mode using takt switches. Let's have a look at some requirements for our clock module. So for the clock we want some different modes, and to make it a little bit easier for us when we are both developing this computer and also debugging it later on, we want to be able to issue single pulses on the clock line. So we need a single pulse module or a regular frequency mode so that we can have clock pulsars coming in a regular interval. And for this mode it would be really nice to have it variable so that we can speed up and slow down the clock pulses that is coming in order for us to validate and debug our circuits later on. Then we also want a high frequency mode, so driven by an oscillator at a fixed high rate. And I am thinking somewhere in the neighborhood of 1 megahertz, like the old school 8-bit computers were running at, like the Commodore 64, and we would like to have some way to switch between these different modes, and preferably switch between these modes in a way that also makes sense. So if we are switching, for example, to a single pulse when we are approaching some interesting things happening with our computer, we want it to not issue more pulses than necessary. So we need a properly debounced switching mode. And that is it for the requirements of the clock modules. So let's have a look into some of these modes and how we can build it on the breadboard. So let's start having a look at the variable frequency mode. So let's have a look at the A-stable or the variable frequency clock that we are going to use. And here I am thinking that we do not need to reinvent the wheel, but instead we can just use the same circuit that Ben Iter developed using a 555 timer. So let's draw out a schematic of the version that he used. So let's just add first our 555 timer box. And let's add the pins. So on the bottom we are gonna have the ground pin. I think this is the convention to do. And on the top we are using, that's pin 8. If we are thinking of the layout of the 555 timer, so here is pin 1 and here is pin 8. So we have ground and then we have power. So let's add this to ground. And let's add this to some power, unlimited power. Okay, and that's our first. Then since, we actually do not need to draw it like that. Instead, pin 4, that's the reset pin, and since we are not gonna reset the clock, let's tie this immediately to to our 5 volts rate because it's active low, meaning that if we are pulling it to ground, then we will reset the clock. Then let's have our trigger and our output pins, and on this side we're gonna have the pin, let's see, pin 6 and pin 5 and pin 7. Okay, so now what we are gonna do is from pin 7 it's gonna go up to the 5 volts, but it's gonna go up through a resistor, and that is gonna be resistor number 1, so R1. And then from pin 6 we are gonna have a new resistor, and that is also gonna be connected to 5 volts. That's gonna be R2, and let's immediately also just write out what these values of these resistors are gonna be. So R1 is gonna be 10K resistor, and that will just dictate how fast our capacitor is gonna be charged. And then for R2 we are gonna have our variable resistor. So this is gonna go from 1K to 1 mega ohm. And these values, I'm just taking them directly from Ben Eater. And of course, he has done a phenomenal work in explaining exactly these values and how the timing is related to these values. And so I don't need to, or I would do a much worse explanation of these values than he ever did. Okay, so let's add in our capacitor that is going to pin number 2, and it's going to be connected to ground. And this is going to be a 100 nanofarad capacitor. And let's add our output. And of course from pin 5, that is up here, and we are going to hook this up to a smaller capacitor as well, and that will also go to ground, and that is a 10 nanofarad capacitor. And this is some voltage regulation that just makes the 555 timer work a little bit more stably. And I believe now we have our circuit. I almost forgot. So this capacitor needs to be discharged somehow as well. And we do that through the R2 and R1 circuit. So this needs to be hooked up all the way on the other side, and we need to hook it up here to pin 6. and of course these lines are crossing, but they are not connected. So I believe the standard for connecting these are to draw these dots as well. So now we have our circuit. So let's actually test it out and build it on the breadboard. This series is, after all, called the Breadboard Apprentice. So let's just make this a little bit smaller so that we can keep it in frame while we are also working on the circuits. Okay, to power the breadboard I have this circuit now, and it sort of fulfills the requirements that we set out for the backplane, that it should be powered through USB. Of course, this is not the circuit that we are going to use later on. But for now, and for the breadboard's version of this, it works very nice, except for this button that is a little bit glitchy. Okay, so let's start by So here, what we said in for resistor 2, we needed to go from 1K to 1 mega ohm. And this potentiometer, it goes from 0 to 100 mega ohm. And just for completeness, we can actually see this if we are hooking it up to this multimeter. So here what we can see, it's at 0 ohm or 0.4 ohms, and if I turn it the other direction, well, now at 1 ohm, 1 mega ohm, and if I now turn it the other way, it goes all the way back down to 0.4. So to have a minimum ohm of 1000, I've just added a 1000 ohm resistor here. So now let's go back to the montage. Now it seems to be blinking fairly slowly, so that is what we want. So now we are at 1 mega ohm, and if we go down, yes, we see it goes faster, 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 and now, yes, it turns. Okay, so now this circuit works. Let's get to the push button or the takt switch or the single pulse generator. So let's first have a look at the circuit that we are going to build. I was not aware before that when you're actually pushing a button like this, that there are something called bounce, that they are going off and on. So if we try to visualize this in a diagram, if we have a axis like this and we have 5 volts here and then of course 0 volts down here. So when we are starting off, it should be then at 0 volts or pulled down, and then when we are pushing the button, it should go all the way up to 5 volts, and then when we are letting go, it should drop back down and remain at 0. But as I understand it, that's not what's actually happening with switches. They are going from, and if we're drawing it out again, so what happens is that once we push the button, it will go high, just as we saw before, but then there is some bouncing happening, and so it will drop down again, and the contact is moving apart, and then it goes back on, and it can of course bounce once more, and of course I don't know exactly how many, and it's probably depends on the quality of the push button, how many times or how frequent these bounces are. And then once the bounce is finally done, it will hold the voltage, and then once you let go, again you can have some bouncing happening when you're letting go as well. So that is not ideal, of course, because each pulse that we are getting here, if we are interested in stepping through a program, for example, in an interesting spot to find a bug or something, then of course we only want one pulse so that we are not jumping over to the next instructions. So we need a way to manage this behavior, and in Ben Eater's case he used a 555 timer again, but in a different configuration. However, and for him he just had the two switches or two modes, so one, the stable mode with the variable clock frequency, and the push button, and thus he only needed one more switch and debouncing for both the switch and for the push button. However, since we have three modes that we want to toggle between, we would need 3 555 timers to do the debouncing then. And at that point it seems to me that there should be some easier way to do this, and I think I have found out that there actually is a different way to do it, and that is with a RC circuit, so where we are using a resistor capacitor circuit. And so that circuit would look something like this, where we would go from 5 volts and we would have a resistor that goes, and then a capacitor that goes to ground, and then here we would have our switch or our tack button. So let's draw the tack button first, and so let's think about how this circuit would act, and let's get in some values just to start with. So let's have a 10k resistor, and maybe for the capacitor here I would think that the 100 nanofarad that was too small before might actually work now. And we will see exactly, there is a formula for how long or this relationship and the timing between them actually is. So let's see what will actually happen in this case. So let's draw our diagram again, and let's say that we are starting and actually this this point is of course going to back to ground. So when we are pushing, we are grounding this spot, and this spot would then be our output again. So here, when the switch is open, this would be at 5 volts since it's a pull-up here. Then as soon as we push the button, what will happen is that we are going to ground here, so this will actually be grounded, this spot. So we will go down, and of course there will be some bouncing, as we said before, when we are pushing the button. And also when we are pushing the button, then we are discharging this capacitor. And of course what will end up happening when the switch is bouncing is that the 5 volt will, or this will be disconnected, and this capacitor will start charging again through the resistor. So we will have some voltage going slowly up, not as sharply as before, because we are charging the capacitor. And then the bounce happens and we will immediately go down again. And of course this can go on for as many bounces as we have, until it finally stays down and the switch is connected. Then once we let go of the switch, we will slowly charge up the capacitor again, and we will go back up to the 5 volts as soon as the capacitor is fully charged. And important here is that we are, since the bounces are happening, we are charging the capacitor a little bit during this time interval where the bounces are happening. But as long as we stay sufficiently low in these small spikes, we will actually not be able, or we will not trigger any pulses, because under 0.5 volts in the TTL logic, that will still be registered as a 0. So as long as these spikes do not go over 0.5 volts, we will always be this will always be treated as a 0. So let's try this circuit out. And now, since the LED here is pulled up to, and what we are attached to the negative lead, or the, is it cathode? No, cathode is the positive terminal, I think, and the anode terminal of the LED. So the LED will turn on once we push the button and we are going down to ground. And of course now it would be really nice if I could show you this working and that it actually is not bouncing anymore. So let's take a look at this signal through the oscilloscope that I have. Of course, I don't want to turn on the oscilloscope in vain because it's quite noisy, and also I don't have a good setup to actually show you the oscilloscope, so we will use my phone for recording this, and hopefully that will suffice for now. And of course this did nothing. This is of course because we are on the rising edge here, and we need to be on the falling edge, since in our case we actually start out at 5 volts. So let's see if I can, there we go, low capacity fingers. Okay, there we go, we actually caught something. So let's have a look, and we zoom in, and actually let's capture another pulse at this lower time rate. So now we are at 50 microseconds per partition, and let's capture one here as well. And yeah, we see that it's actually working pretty nicely and no bounces. Let's see if we can capture one longer again so that we can see the rising edge, and let's be super quick in our push. So super fast fingers. Okay, so let's zoom in, and again what we see is that yeah, it immediately goes low when we push the button and then stays low. And if we have a look at the when we let go of the button, yeah, we see again that there are no bounces. And okay, and of course now we need to test the button in without this capacitor, because if we have a look at if we were to remove this, it's just gonna be the same as if we just had the push button, and we would actually see the bouncing again, or presumably we would see the bouncing again. So let's remove that and let's trigger. Oh, and now we need to, of course, we need to switch the time scale again. So let's go back and there we are at 0, and let's go to 80 millisecond once more. And well, what we see now is that there doesn't seem to be any bounces happening. Let's zoom in a little bit and we capture. There we go. There we actually got a bounce this time. And here what we see is that it immediately shoots up, and that would actually trigger 2 pulses, or 3 pulses in this case. No, 2 pulses. And that is definitely not something that we want. And then we can see we have something going here as well. But what we also see is that these pulses or these bounces are very short, and that's why we most likely will get away with using a very small capacitor, even though we are using a 10K pull-up resistor for this, because these will be so short in charging. Yeah, and so let's put this back again, and actually let's pause the oscilloscope. So now that we have seen that this circuit works, I wanted to go back to the circuit itself one last time, because I am sure that some of you will rage against this circuit. Why? Well, let's think about it. So what will happen when we are actually pushing this button? Well, this will be shorted out, and so the 5 volt will go through this resistor, and since it's a 10K resistor, it doesn't pull much current through to the ground. But our capacitor here, it is very small, but it's technically a dead short against or through the button here. So I believe the best practice would be to also input a small resistor in this circuit. So let's do that as the last thing. So okay, so now we also need to think about our high frequency circuit. So, and here it is since these are oscillators, they are actually very straightforward. You just apply power and ground, and then it will output a steady oscillation with a very nice square wave. let's do that. Let me just pull up the datasheet for this one so that we are actually hooking up. I'm fairly confident that it is on pin 4 that we need to apply our voltage, and then at pin 2 that we are going to ground, and then at pin 1 we have our oscillator. Let me just double check this. Okay, so here is the datasheet for this oscillator, and let's scroll down to the circuit diagram. So here we see that 14 or 8, that should be going to our 5 volts, and then pin 7 or 4, that should be go to ground. Pin 8 or 5, that's, and then pin 1, that is input, enable input, or no connection. So that is, let's not connect this then, and pin 8 or 5 should be our output, I guess. Okay, with that straightened out, let's try it out. So we hook up power to then ground here, and we should have our signal coming out here. So let's just double check with our oscilloscope again. And now I feel silly that I took down this distance. Hopefully it will be easily assembled again. Okay, so let's take the probe again and of course this is going to ground. Let's hook up the ground here so that we can see it. Okay, now this seems like awfully noisy, and I do not think that this is entirely correct. So something is definitely going wrong here. Let's go back again to the Of course, this might not be the best way to work with power going on, or with power on the circuits. But let's see. Okay, so that definitely seems like a much more stable circuit. And let's trigger it. And now we are, of course, again at and of course we do not want this to be on. Okay, so we are at 1 microsecond per clock pulse. So and that is of course at 1 megahertz, and we see that now the signal goes all the way from 0 to 5 volts as we want it. I don't know what was wrong before. Clearly, just resetting these components somehow made a difference. Anyways, that's it for now. Let's turn off the instruments, and also let's turn off the oscilloscope.